Take it away.
All right. All right. Thanks, Ken. Um, just briefly, before I go any further, I just have a little flashback. Um, 43 years ago, I think back in 1982, I gave my first talk at the Ashley meeting around the time of the year. What I was talking about it, I was talking about hypersensitized kit film. It's a forming gas that helped to boost up the film speed. Now I brought in the bit box. I took everything out, all the hoses there, and the cylinder, the gas chamber, the hand pump. I turned the room into a laboratory, and it's just amazing that since that long ago, and
What year
it
was that?
was in 1982.
Wow.
Yeah, that was the first year when they have the hypersensitized film, where you do a lot of deep sky observing and imaging, not imaging, astrophotography. Yeah, they don't call it imaging at that time, they call it astrophotography. So tonight, it's amazing, I'm still standing up here. Uh, talk about the same thing and also, anyway, I hope I'll be up here for another 43 years. Who knows? Okay. All right. One thing I forgot to mention, last night, I had a fantastic view of Mars. Now, we all know that there's smoke in the air, and we all know that it causes, uh, 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 you know, makes the sky look a lot dimmer with less stars and all. But I have to tell you, I admitted that when there's smoke in the air, it's great for planetary observing, but bad for deep sky observing. Make a long story short, I had a good view under the high power. I mean, it was dim. Mars was barely visible naked eye. It was dim, but on a high power, it's dimmer, but it's more crisp and nothing, no glaring, nothing, and you can really see it clearly. It was just, it was a little slight turbulence, like pumping in and out, but no winds. And so great. I had a really great view through the 10-inch telescope, high power. Then I managed to take some imaging, which I posted early today. I don't know if you see it, but you can clearly see the detail. Mars is 5.5 arc seconds, so it's really, really getting smaller as it's moving away from Earth. But over the years, when we have like the Canadian wildfires or Rocky Mountain wildfires, that's then we get smoke in the air, and I remember to see all these planets. They really had a good view. And for example, back in 2020, um, just 3 weeks before Mars opposition, um, Mars was barely visible naked eye, even though it's at the brightest Jupiter, -2.5. And with that smoke in the air, it dimmed down to almost second magnitude. It's the only star visible in the whole sky. The rest of the sky was just black. It's just like it's nothing there, but Mars was just dimly visible and had a crisp view and on. Not only that, but Jupiter too and Saturn. Um, when when you see those things like Mars, you see the polar caps, you see the clouds, you see the albedo features, you see the dark area or bright area. In Jupiter, you see the band, the belt, the zone with fantastic detail with a great red spot, and you have the magnificent ring of Saturn and all. So when you look through the telescope, you see all these features there. And what about Venus? Well, Venus is so-so unless you follow the face from crescent to half to gibbous and all face. Okay, what about Mercury? It's very rarely you get a good view of Mercury. I talked to a lot of people. They always say that they've never seen Mercury, and they have to see once in a while when it's very low to the east before sunrise, or very low to the west after sunrise. Um, if pick up any book on astronomy, turn to a chapter on Mercury. Is that encourages to go out and look for it? Probably not. I've talked to a lot of people, especially at the Star Party, like cellophane. Almost every time I'm at cellophane, when I talk to the group of people, the planetary observation there's always comes up, and I told them that have you seen Mercury? And no, well, they say that it's always too close to the sun. I have a 14, 20-inch stop. I don't want to point too close to the sun. It's never visible where the telescopes stay because they always have trees and houses in the way, and I have to move over there, and it's too heavy to move around. So I hear that a lot. I told them that well, there's certain things you can see on Mercury, but it's that Mercury. It's one of the neglected planetary planets. It has the reputation of being the most least observable planet in the solar system. Um, so, make a long story short, I became Mercury coordinator for the Association of Lunar Planetary Observer, which is also known as ALPO. My responsibility is to collect the observation from the members and analyze it and report to the journal. Now, the journal publishes every 3 months in quarterly period. And you see my article about an apparition report, and I have my own column about observing Mercury. Any members did outstanding observations, something like that, and I reported to the journal. I have my own column in addition to my annual report, Mercury. So what I like to do is be gladly to present my talk for tonight, the nature and observation of the ray craters on Mercury. So I just want to show you, give you an idea, what it's like observing Mercury. So you're not going to see just a blob, just a small little thing, or maybe just a little phase. You see Mercury as the real world with details on it. And as of 50 years ago, professional astronomers with large telescope cannot even able to do this. What an amateur astronomers can do today. It's quite amazing. So this is probably what you're going to see. It is one of the best images that you ever seen of whatever been around. Now, not because of my image, but other members also. And so I'd be very happy to present to you. So the title to talk is The Nature Observation of the Ray Craters of Mercury. Now, this is not about observing Mercury. It's about what details we can see through the telescope under the proper condition. Okay. How do you advance this? It's not working.
Oh, it's because you have Zoom open in front.
Okay. Okay.
You've also paused the slideshow, so I'll say resume slideshow.
It's a line, we have rotation.
There we go.
There we go.
Okay. All right. Now what you see here, this is the map taken by the global view was taken by the Messenger spacecraft, which is orbiting around Mercury between 2011, 2014, or 15, 4 years orbiting around Mercury. And this is a very global shot, taking a different kind of color light to distinguish between the ray craters and the background. As you can see, all these white spots, these are the ray craters, and that's what I'm going to talk about. Okay, the ray system. Well, I'm going to be talking about, the craters here. And what you see here, there's one particular crater that has rays here, there, and there's another one right here. This one here and have rays here. So even though there's some other craters here, but they're not, they old probably, they're not producing any rays, but they have a heavily impact there. So that's what I'm going to be talking about. So. Okay, what is a ray system? Well, let's break down the information. Now, a ray system comprises radial streak of a finely ejected thrown out during the formation of the impact crater, looking somewhat like many of thin spokes coming out from the hub of the wheel. So you have, like you have the wheel here, you see spokes like here, something like that. And in the center, it's the crater, and you see rays here. So it's look like a cartwheel, something like that. So that's just a simplified definition. So here's some additional information about the ray craters, so they're able to break down. Crater rays are some of the most striking features on the airless world. Now, when I talk about airless world, talk about the world without the atmosphere. What I mean by without the atmosphere is that if there's an impact, there's no friction, no dragging. It's just straight down to hit the surface with the impact. Hit the surface in an airless world. So, the system of bright rays are quite conspicuous under the high sun, which give out very high contrast, so you can see it well from the distance. The long major rays are complex and usually not exactly radial. Well, that means that if you look at the crater, impact crater, you may see the rays on one side, but not on the other side. So it's not fully uniform. So, it depends on the angle of the impact. So just maybe one side you can see the large impact rays or something like that. So that's not completely round. Conspicuous ray systems are not necessarily related to the large crater. So when you see a large crater, it's not necessarily you're going to see ejected rays. Even the smallest craters, they have these rays there. It depends on the impact, and the age of the rays. Rays are more easily seen in optical wavelength, but they have also been observed in the radio wavelength. So visually, you can be able to see the ray crater, but even in the radar wavelength, which is not optical, but it's on a wavelength system, and you can able to map out the crater. Same thing with Magellanic spacecraft around Venus. You cannot see optical, but they're able to, the radar able to penetrate to the atmosphere, and they get the surface detail. And same thing, that they're able to make it out the crater. So same thing.
Frank,
Yes.
do you know why radar picks it up? Is it because the rays are
It bounces, yeah.
Right, but are the rays thick enough to be a
Well,
height
they
difference,
pick it
or-
up the pattern.
Okay.
Yeah, and the rays bounce it up, and and form a pattern. They can able to distinguish between the surface and the crater, and you see the bumps and all, and it has to be cratered. So, yeah. So the same thing with Magellanic spacecraft around Venus. It's the same kind of job that they did with the radar wavelength. They are among the youngest features on the surface. That's why they're so bright against the old surface. So they give enough contrast to be seen. Okay, now let's start with the moon. Are we all familiar that the moon does has ray craters, like Tycho or something like that? So these are my pictures. So you can see the full moon. I don't know how well can you see from here, but you can see all these ray craters there. So even the moon here, one there. We can look for individual craters. You get more detail. There we go. That's a Tycho. Look at the ray craters here, all the way up here, even beyond the frame, all the way down here and there. So that's the velocity or the impact probably was very great. So I'm going to talk a little bit about that also. Even on Tycho, the close-up, even if you look at the close-up, you cannot see the rays too good because you only see just the crater itself, but you need a wider view to see, and then you can see that it's stretching across the face of the moon. So, Copernicus, it's another perfect example. Now you can see the rays easily. Here, over here. So they're pretty much uniform when they're doing the impact. So the airless world, like the moon, they have the greatest impact without any atmosphere. Now in with Kepler, you can see the rays there, all around here. So So these are fine examples that ray craters that can be seen on the moon. Now, even like I say, even the smallest crater, like that, they have rays here. Here, this is from the Lunar Pioneer, and you can see the surface kind of dark here, and with a very relatively young impact here, it makes the greatest contrast against the surface background. So, okay, even Ganymede, Jupiter's largest moon, have the ray crater and can be seen right over here. And this is the image was taken by Windows Simulator, and this is where, at the time I was observing, that's what the surface of the moon is supposed to look like. And this is my image here, and you can make it out the ray craters there. Yeah. Now, I supposedly believe that, like Mars is the best planet to observe the surface. Mercury is the second best. What's the third best? Now it's debating between Ganymede and Venus when you observe the infrared light, when you penetrate to the atmosphere on the dark side of the surface, on the dark side of Venus. So now it's debating whether this is the third best or Venus is the third best. So this is taken, when the scene was very good here. This is the largest ray craters on Ganymede, so they're able to pick it up even with a 10-inch telescope under the best condition. So. Okay, now on to Mercury. Okay, here we have the moon and Mercury. That's a quick view. I talked briefly about the moon, now how to compare it with Mercury. Well, even the moon had ray craters, like I explained before. Then here, Mercury here had ray craters, and over here. And you see a Tycho ray here. Usually, I don't know how well you can see, but it's almost a stretch across halfway in the moon. But even here, some rays here from these ray craters. You know, hit one here and there, but right there. Okay. If you have a quick view, Mercury is similar to the moon, correct? All right, but if you look carefully, there's some differences between the moon and Mercury, and I'm going to talk about that. Okay. Now I have some additional information about the ray craters, that the crater ejected ray are the most common feature on the surface of Mercury. Because there's a lot of them due to the surface condition, which is Mercury appears darker and have a lower albedo features. So with the ray craters, it appears very bright, and it can see well from the distance. The moon has some brighter areas, so they have fewer ray craters, as we can see. But yes, like they are visible as white spots. They may be similar to the moon, like I just showed you before. The ejecta is intense due to the stronger gravity on Mercury than the moon. Well, the moon Mercury has a stronger gravity than the moon. So I'm going to explain that briefly, what the difference between the two when there is an impact. Because of Mercury's much stronger gravity field, ejecta will travel more than twice as far at the moon than on Mercury. So if there's an impact on the moon, the elements, dust and elements, they can shoot out very, very far away across the moon. But Mercury has a strong gravity, so when there's an impact, the element won't go as far as the moon. It would stay more condensed in the same area. So that gives us the stronger contrast, and it appears brighter. It's more
Frank,
condensed.
I don't understand why Mercury has greater gravity because the moon is larger.
Well, Mercury and the moon it's almost the same size. Well, I think Mercury is a little bit bigger than the moon.
Oh, okay.
But Mercury has a stronger gravity, though, than of the moon.
I'm sorry? Oh, more density.
Yeah, it's more massive
Right.
than the moon. Yeah, I'll show you again. Yeah. Mercury has the intense interaction from the sun, such that the heat, radiation, and the solar winds due to the space weathering. Now, even the moon has a space weathering, but Mercury is much closer to the sun, so they have a very intense heat, radiation, and the solar winds from the sun, and they make the surface to be a little darker over the period of so many years, and appears darker. So when there's the impact crater, which has happened maybe in later time, it's appear brighter because it's fresh and it hasn't been exposed much to the space weathering yet. And so it just appears brighter, and you have a very strong contrast against the darker background. Because the ray craters are relatively young, with a little effect from the space weather. That's what I was talking about. So even the moon too, but the moon is much further away from the sun than Mercury. So even the moon has a very small effect of space weathering too. Okay, now Mercury's gravity is more than 2 times that of the moon. Okay, like I said, let's pretend there's an impact on the moon right here. It comes straight down. This is the surface, and the moon, the impact comes straight down. Now, all the elements, dust and elements, can travel this far away. Here, can travel this much far. Now, compared to Mercury, which has more than 2 times the gravity, and the impact comes to the surface right here, then the dust and elements can shoot out this far here. So the stronger gravity. So most of the ray craters on Mercury are a lot smaller compared to the moon. So that's a bit difference there. Okay, craters with bright rays are thought to be relatively young because the rays are still visible, indicating that they have had less exposure to such weathering processes than craters that have lack rays. So that's what I was talking about. Space weathering. All planets are affected by space weathering. Don't forget, even the Earth, but the Earth has the atmosphere to protect it. But I'm talking about the airless world, the world that has no atmosphere. And they have the strongest space weathering. So, due to the heat, radiation, and the solar winds from the sun. So it's making a little effect here. It makes the surface a little darker. So after so many, billions of years or something like that. And so with the impact crater, which is younger, and it's more fresh, and it appears brighter, and it's less effect of space weathering. So that's why it appears brighter and a stronger contrast, and you can see from the distance. So okay, all right. Here's for example. Now, when I do my observation of Mercury, this is my location where I live. This is a 10-inch telescope here. Now, this is where I do my Mercury imaging, usually in the morning. That's when I find it best. Now, looking down there is south. This way is west. Toward the building is east, and behind here it's east. So at the time when I do the Mercury observation, the sun is behind the roof, and Mercury I just wait the time when Mercury clears the roof, and I have a short window opportunity to do observing and imaging Mercury. So that would be the best time during daylight. Now, when I show the images of Mercury, they're all taken at daylight. So now let's point that later on. So this is my setup. Usually my setup, and I can go a little further out toward the grass here. I can go further out, but my computer, I don't have a laptop, but eventually I will get one. My desktop computer, the inside the living room right here, and I have cable wire to run here. So I can go no more than 15 feet away. So this is an ideal spot right here. So I can go further out, And I can do that, but I need a longer cable wire, but I don't think it will work. The camera will work. So I can control the hand paddle. I can control the hand paddle from inside where I can observe in front of the screen, and I can do, do the imaging. I can focus and centering and so forth. So so that's the best way to do it, the imaging Mercury. So, and you can see that once the sun clears the roof, then you have a sunlight here, then it's over. Then you get the heat wave effect, then you get the heat from the sun, then you get more light scattering in the tube. So that's the end of the session here. Yeah.
Say, when Mercury present before the sun, you said it's a short period of time.
Yeah.
How short a period?
Well, if it's like near the greatest distance from the sun, which is no more than 28 degrees, I have about maybe an hour. If I'm lucky enough, a little more than an hour. So before the sun passes over the roof. Because you have to be in the shade. You don't want to be in the sunlight where you observe Mercury, then you get a lot of glaring and all. So in the shade is the best way to do it. And Mercury is high in the sky. Where the telescope is pointing, it's right near the meridian, the highest point as possible. All right. You don't want to observe Mercury when it's low in the sky, because then you have looking through the long path of the atmosphere, and you get the blurry images, and you won't able to see well, especially when it comes to imaging. You're not going to get anything. So Mercury has to be really high in the sky if you want to get most out of it. If you want to capture the detail on the surface and using the filters, then you're on the right track in doing it. So just to give you an idea, this is the setup. Okay. All right, here's some imaging. I'm not going to show every one of it, but here's I'm show you some of the images that show the ray craters. Here we go. Here's the white spot right here. That's the ray crater. All right, this is my imaging, and this is the imaging from the Messenger spacecraft with Zippo's simulator. And this is what Mercury should look like the day I was observing, October 15, 2022. And very, very, very similar, striking similar. Yeah. This is the ray craters. Yeah. Another one here. This one is the ray crater here. And you see another one here near the limb. And it's right here. And you see a few more right here. Yes. So just to give you an idea, that's where ray craters can be imaged. And also here, use the red filter. Very important. This is taking the daylight. Don't forget. All the images you're going to see are all taking the daylight, even though the background is dark. But you have the red filter to increase the contrast, and in addition to increase the contrast on the surface. So you have a double whammy, and that's the best way to do it. They were taking out 14 hours, 20 minutes in universal time. It's converted to the local time is 10:20 in the morning. No, I'm sorry. Yes. This is not the daylight saving time. Yeah. Yes. 20 after 10 in the morning. It was almost close to the meridian, the highest point as possible. Okay. Another member, Gregory Shannon from Florida, got the 10-inch telescope, and I try to encourage the image of Mercury and all, and I was sort of like a mentor to help him to get the most out of the imaging. So this is my images, and this is Gregory Shannon image, and this is a messenger image. Okay, and this is the day that this is what Mercury should look like the day we're observing, October 16, 2022. Now, also a blur at this longitude. It's not sharp, but there's a little blur. What I did that to degraded the image to equivalent to the amateur telescope, the resolution of the amateur's telescope. So that's why it look a little more similar there. Okay, here's my image. Here's the ray craters here. You got one here, one there, and also you took two here. So we have a nearly simultaneous observation. You've taken in the morning, 11 hours, which is about maybe 10, maybe like 7:45 in the morning. Mine was taking a little later, take 10:30. So that's about 2 hours difference. So he took when it Mercury was low in the sky. I took when it's much higher in the sky. So you can see mine is a little bit better because it's got a better resolution. The higher the sky, the better it is. So, yeah. And also you see some dark features here, beetle feature. It matches very well here, and he got captured the same thing too. So that's pretty well done for this. We also the idea is to have the observation at the same time we can confirm one another what we saw. Okay, here's another perfect example. Now Mercury is almost full. Almost a full face. Here's the messenger image. Here's the two ray craters here. And here two ray craters here. There's another one right here. It's a very faint one right there. This one is the same as this. What happened was why this is fainter, why this is brighter. It's probably due to the solar angle. Now, I don't know exactly when this image was taken, when it's very low in the sky or high in the sky or high noon, but the image was taken almost high noon. This is noon I've seen from Mercury's surface, and that's why it appears brighter. And you see several more here, two here, 1, 2, 3, 1, 2, 3. Here's the dark albedo first, which is right here. So that's what it is, that you can able to determine what can be imaged and how many ray craters can be imaged on Mercury. It's not a perfect example. This was taken October 9, 2023, almost 2 years ago. It's almost a full face, 96%. Now, when I talk about a full face, that means Mercury behind the sun, but it's about maybe 10 degrees away from the sun. So it was safe enough to do some observation. And you have a very short window, shorter yet, and everything had to be quick. You can't lose any time. Every minute counts. When Mercury cleared the gutter, clear the roof, and you only have a short amount of time before the sun cleared the roof, and everything had to be quick. And luckily, the scene was good, and I was able to capture more ray craters here. Here, this one I showed to you. It's another one right here. This Kepler, and this all this. There's another one up here. This one here. So, yeah, that's quite a few ray craters that can be imaged, even a moderate size telescope, a 10-inch. As long as you have the red filter, it makes a lot of difference. So now, if I used without the red filter, the 610 long path, without the filter, probably I did it once. It's kind of washed out, and it's poor contrast. So this is the best filter to use. So,
Right?
yes.
Filter a standard like RGB.
No, it's better 610. That's the long pass filter. So everything was blocked before 610 nanometers, and then you have light coming in after 610. So it's like this way and all the way down to the infrared. The blue light that blots off. All right, even if it blots off, you don't see any light around here because the blue light being blocked by the red filter. So it's just almost like nighttime. Yeah, that's amazing. So that the filter is the way to go to do this kind of work. Okay, now I have enough images to create a short animation. This is by Gregory Channer, the one I was just talking about for Florida, and this is my image, and I did combine together, and we have about 9 images. We have 9 images of Mercury, the same apparition during the October 2022. And you can see when Mercury was slightly crescent and all the way to full. As you can see, the ray craters moving across the disk. From you can follow one here, hit one here, and getting closer here. You can see here it appeared before it to be on here. Then as the face advances, then you can see it move close to it. Now, this is not the rotation of Mercury. This is the orbital motion as Mercury going around the sun as seen from Earth. Now, the actual rotation, you can barely make it out. Mercury takes about 88 days to around the sun, but the rotation itself on the axis is about 58 days. Okay, yeah, 58 days. So, in other words, when Mercury completed 2/3 of the orbit, it's one rotation. I see from the sun. No, I'm sorry. I'm seeing if not from the sun, but I see, yeah, from the sun. Yeah, it's a little confusion because is it doesn't correspond with actually revolution around the sun, and it's 2/3 of the orbit to complete one rotation. So, in other words, Mercury rotates 3 times when Mercury went around twice around the sun. Okay. Now, if you look carefully, you pick up you just look at one ray crater. If you look carefully, you can see it getting closer to the terminator as Mercury moves around the sun. Now, when it gets close to the terminator, that's the actual rotation. That's the actual rotation as Mercury advanced here, because it looks like it's moving well with the terminator, keeping pace with the terminator, but it's moving a little faster, and that's why it takes 58 days to run the sun. Now, that's kind of hard to determine the exact rotation the way you see here, but they have a very slight change. I have another image that you can see a little bit better. Okay, here's another one. Now you can see here more ray craters here, and you can see advance and then reverse, then forward, then reverse. You can see it, the date here, the time, and the degrees here. So that's the best way to do it, because that way it's more eye-catching to see the details of Mercury, especially the ray craters. So I was after the ray craters because I like to see how many ray craters I can see compared to what the image took by the messenger spacecraft. Okay, here 2 days animation. Mercury was almost full, almost a full face. As you can see, it's rotating from left to right. Again, it's not a rotation, but it's an orbital motion as seen from Earth. So, and you can see how many ray craters here. You can see 1 here, 2, 3, 4, 5. It's the faint one, 6. So approximately 6 ray craters you can see on the full face. And secondly, you see more detail from half to full than when it was crescent, because when it's gibbous between half and full, Mercury's exposing much of the surface, and more details can be seen despite of the smaller disk, because it's almost on the far side of the sun and it appears smaller as seen from Earth. Okay, let's take a look, closer look at the ray craters. You can see the ray craters are Debussy. It's about 50 miles diameter crater. As you can see the rays here. Yeah, that's a close-up. This was taken by the messenger spacecraft when it's orbing around Mercury. And this crater is this one right here. It's a close-up here. You can see how intense it is compared to the surrounding area. That's why it looks so bright, because with the space weathering, all this old surface exposed many, many billions of years of space weathering of radiation, heat, and solar wind. And this is relatively young. This is probably much younger in age compared to the surrounding area. So that's why it appears so bright, because it's fresh. And that's why it gives more contrast. And you can see well in the amateur telescope right here. Now, in the old days, like Schiaparelli, Lowell, they observed Mercury too. They study Mercury all their life and never come out with the conclusion why with all these spots. They believe the clouds. They don't know. So luckily we can able to find out what they are, and they never come to conclusion what they were back then. So yeah. So luckily, now even the amateurs side telescope can able to do something like this. Like I said before, a professional astronomer as of 50 years ago couldn't produce any image like this yet, even with the larger telescope. So this is quite amazing. Okay, another ray crater, I mentioned, this is the combination of an Ellerton crater and its neighbor. So it's the combination of all these craters here. I don't know which one is Ellerton, maybe the largest one or this one. You know, it doesn't specify whether, but as from the distance, everything merged together, so it looks very bright. So this area here corresponds to this spot right here. So, yeah. Okay, and so from the distance, you can see that it merged into like a bright spot, and you can see the image right there. There's another one, this one corresponds to this crater. Now, this doesn't look too bright, but they have the surrounding area look a little brighter than it should hit the older crater, but it has more reflectivity than its surrounding area. So this appears brighter, but not as bright as the other two ray craters that I show you. But it's still fairly bright here. It depends on the solar angle. And so when it's high noon, in certain solar angle, it appears brighter than other. Somebody have the ray. Yeah, Rich.
Hi. Is any difference between surface material and the material that's found in the crater or in the ejecta?
The surface here is considered a very old element there, but with the impact, they have fresh element. Okay, when at the impact here, all the fresh element exposed in the sunlight and to give very bright appearance, and to compare the surrounding area, which is what's made of, I don't know if that's the name of it, it's a certain compound, so it appears darker due to the space weathering. So that's why there's fresh material from.
So that's basically, it's basically all the same compound?
Probably, yes. Yes. Yeah. Okay, here's another angle. This is on the north side. This crater is Hakushia. It's a Japanese name. Crater 15 miles diameter. And this one here is another bright area, but I'm not too sure if this is the ray crater or this is the bright point. I'm not really sure. So it's a known crater or Apollinaria albedo fissure, which is the area right here. But I'm not sure if it's the ray crater. They don't have a name yet. So this one here corresponds. It's right here, right along the limb, and it's a bright spot right here. This crater, Acusia, it's got the very large ray crater here. That must be the heavy impact. So, and it's on the north side here. And that's why sometimes Mercury has a bright cap or something like that. So that's maybe due to the bright ray craters, which was unknown back then. So there's a very good chance that some of the early observer back in a century ago that see that Mercury had the bright spot there, so we don't know if it's a cloud or something like that. So this might be a ray crater at that time, which was unknown at that time. Okay, here's another one here. Now this is very center. This is almost full, so this is high noon, I think, from the Mercury's surface, and this is probably this one right here. Warhol, and it's unknown crater, which there's no name here, but this is a crater here that probably produced a very bright contrast under the high noon of the sun, visible from the surface of Mercury. So they give it a very bright appearance, and you can see here, right there, right in the very center of the disk. Here's another one. This is the brightest one. This is Kuiper crater, 30 miles diameter, which is this one right here. And on top of the old crater, you can see that the older crater is much older than this impact right here. So that's what I mean. It's fresh impact here with all these rays here. So this corresponds to this one right here. Right here. And you can see how many more ray craters, yeah, all around there. So the next one, I really don't know which one is this. This is unknown craters and region. according to the map here, where the disk should be visible, at the time I was observing, there is a bright spot right here, and this corresponds this area right here. So I don't know which craters here or this one here, but this is the combination of this area right here, and it appeared very bright and certain solar angle I seen from Earth. Okay, here's another angle here. The messenger image, the day I was observing on March 21st, 2021. Here you see these ray craters here in the north, in the line here, which corresponds to this one here, and that there's more ray craters appear here. So you can see how many are they? It's a quite different. There's another one right here. There's a faint one right here, which corresponds to this. Yeah. So that's where we know what you capture there on the image. Now I can break down the name of it, which is kind of hard to pronounce, and these are the ray craters here correspond. Here it's 3 ray craters in the line, north and south line, and you can see right here. And I don't know which one it is. It's kind of a very bright spot right here, which corresponds to this one here. This is unnamed crater. I don't know why it's such a prominent crater. It doesn't even have a name yet. So this is the Eastman and Mellilo. This is Mellilo, and unnamed ray craters or Amaro, something like that. So yeah. So this is the portion of the surface that's visible here. So we know that we have a lot of ray craters that can be imaged from Earth. All right, here's another perfect example. This one here, this one, the bright one here, 2 here, you can see here, there's several more up here, there. So there's a lot of ray craters. Under the best condition possible, the scene was pretty good at that time. It was almost close to excellent. Excellent would be very rarely have excellent, perfect conditions. So it was almost perfect. So I give it 8/10. 10 means best. 1 means worse. So it was pretty good at that time. At that time, it was 5.8, so it's kind of small. There, 77%. So it's like a fat gibbous there. You can as seen from Earth. Then I break down the name. You can see which is which. Yeah, it's a faint crater, Bartok, is here, which corresponds to this one here. And there's another white area, another ray crater right here, which corresponds to this area here. But there's the ray craters here, right here, or this one here. So it's just a bright area. So I'm not sure which one it is. So it's just like a bright spot right here. It's just combined here. There's another one up here. This is Degas. It's another impact ray crater, which corresponds to this one right here. And this one here, part of the combination of 2, which corresponds to this one right here. So you can see several bright object features here that you can see on Mercury. So, okay. Now, there's a spacecraft on the way to Mercury because Pepsi Colombo mission to Mercury. So it's on the way there right now. And so what is Colombo, Pepsi Colombo? Who is Pepsi Colombo? So it's a name after somebody, right? Well, okay, Pepsi Colombo mission is named after Giuseppe Pepsi Colombo from 20 to 1984. He passed away over 40 years ago. He is a scientist, mathematician, and engineer at the University of Padua, Italy. He was the first person to propose the interplanetary gravity assist maneuver using the 1974 Mariner 10 mission, which is now bears his name. So you know the words that instead of like Mariner 10, instead of just fly by Mercury, they used the gravity system from flyby Venus and Mercury quite a few times, because as you headed toward the sun, it tends to speed up the spacecraft. So they needed to slow it down. So they used Venus tragedy, flyby, and Mercury flyby in order to get this almost the same velocity speed of Mercury and even for Venus too, but there's more toward Mercury. Also, it's a technique now used for figuring by planetary probes. Now the standard they use gravity assistance on the way to certain planets. Now, if it wasn't for that, they need a lot of fuels. So by this way, you save a lot of fuels. Now, Colombo studied the planet Mercury, and it was his calculation which showed him how to get the spacecraft into a solar orbit, which would encounter Mercury multiple times. Not in orbit, but just a flyby at that time. Using the gravity assistance maneuver with Venus, a flyby Venus, and that's why it slowed down, another flyby slowed down yet, and it hit Mercury, and also Mercury slowed down yet until, it's not intended to orbit Mercury, but it's just a flyby, so they can use multiple times. It accomplished three flybys of Mercury instead of just once, instead of just go by. So they're trying to go around and use Venus again to slow down, and use Mercury to slow down. So that's why you can do multiple at a time, and you save fuel that way. It was the first spacecraft to use the gravity assistance. Since then, the techniques have become common. So, now, Petri Colombo, it is the joint mission with European Space Agency, ESA, and Japan Aerospace Exploration Agency, JS. So you have two countries here. Unfortunately, United States is not involved with this spacecraft. The probe launched on October 18, 2018, so it's already 6 years on the way there. It would take 8 years. Now, unfortunately, it's supposed to arrive this year. It blasts off 2018, take 8 years, and it's supposed to arrive sometimes, well, 7 years, well, it takes 8 years, 7.5 years, But what happened was there was some kind of glitch. It's originally supposed to arrive the end of this year, but there's some kind of glitch, so they have to delay another year, so it will arrive there at the end of 2026, the end of next year. Now, the probe did many flybys with the Earth too. Yes, I forgot to mention that. It fly by the Earth too, Venus and Mercury, to reduce the speed as it approaches closer to the sun. Like I say, it tends to speed up as you get closer to the sun, but it needs to slow it down. Without any fuel, you need gravity assistance. Otherwise, when you're using fuel, it's going to cost a lot more money to operate the spacecraft. Now, it has 3 components. Mercury transfer module, MPS for propulsion, Mercury planetary orbiter, and Mercury magnetic orbiter. So, in other words, so when the spacecraft reaches closer to Mercury, it's just going to separate. One go this way, one go that way. This one will probably go polar orbit. They do different scientific experiment. And it's better to arrive in Mercury orbit in November 2026. That's just I mentioned before the end of next year. Okay, what you're going to see here, you can see what is launched. You can see how many times it went around the sun and it fly by the Earth. This is the Earth, Venus, and Mercury. And you can see how many times it went around and how many times it fly by the Earth and Venus and Mercury also, in order to slow down the spacecraft. And it takes 8 years to do that, to save fuel. So after so many times, now you start to get a little, lost around here. But I'm going to show one more time, and you can follow it. And once it reaches here, now you can see it's reached there, and here's the time here. It's supposed to be 2026. Yeah, here it goes, blasts off, and it's staying around the Earth orbit. And at the flyby again, if you look carefully, here, flyby again, and then it goes inside there to see it's speeding up a little bit, but you need the planets, Venus and Mercury, to slow down the spacecraft. So I'm going to show you one more time to finish here. So after so many times, you're trying to follow, then you start to lose it because then you get very crowded around here. So. All right. That's it. Okay. All right. Now, on the way there, the spacecraft, Mercury Colombo, did the third flyby, and this is the image of Mercury, and this is part of the spacecraft. And here's it's just a flyby, and here's the image of Mercury. Now, compare my image. This feature here is the same as this one, but this is on the dark side. I have this portion here, and this was on the dark side, and only this part of the surface visible in my image here. So we captured the same thing. So this is almost similar to the resolution of the amateur telescope at that distance. So that's quite amazing that whatever's captured this parts of the surface, it can be seen here. You hit this one right here, that's taken from the messenger. This one here, it's the same part of the surface here. These are ray craters here. This is the same thing here, and see here. But this is on the nice side here, as seen from the spacecraft here. Nice side. So this is part of accomplished. This when you can match a flyby image with the image. Now here's another one. Now this is Mercury Colombo last Mercury flyby. Now what you see here, is this is the North Pole. This is the north side of Mercury, and the spacecraft went over the North Pole and looked down. So you visualize that that's what Mercury looked like, viewing from above, looking down. This is the northern hemisphere, and you can see these two features here: dark craters, the double dark crater, and another ray craters right here. This circle here, it corresponds the same feature right here. Now this is view from Earth. This is view from above, taken by the spacecraft, and you visualize the spacecraft over here. Image is pointing down this way. It's the same thing on this side here, and these two images right here. This double floor crater and another ray craters here, and you can see right here, the same thing here. So that's quite accomplished. That whatever the spacecraft get images and just major features here, it can pick it up in the image right here. So this is going to be published in the Apple Journal. So, okay, the final message. The Apple Mercury session, which I'm a coordinator, will continue to collect observation from the members. There, how many injected ray craters worldwide can be seen in the amateur telescope? Well, I just demonstrated that it's quite a few, but maybe there's still more yet to be imaged. So I'll keep doing it, and let's see how many ray craters can be captured. What are the brightest ray craters? So I show you some of the brightest ones, depending on the solar angle, and depends the angle I see from Earth. So far, most of the ray craters are visible from Earth. So I just demonstrate and show you that it's quite a few. Yeah. Okay. More work is needed. So if you ever plan to go somewhere, that's it. Oh.